Hello everyone, I'm Divya Srivavi working as Assistant Professor in the Department of ECE, SJBIT. In today's video, I'll be discussing about the pulse code modulation. With the sampling and quantization process, uh, now we can easily understand the pulse code modulation. It is basically the most basic form of digital pulse modulation. In PCM, a message signal is represented by a sequence of coded pulses, which is accomplished by representing the signal in discrete form in both time and amplitude. The basic operation performed in the transmitter of a PCM are: one is the sampling, quantization, encoding, and this is with respect to the transmitter. A low pass filter prior to the sampling is used. It is included to prevent the aliasing of the message signal. The quantizing and encoding operations are usually performed in the same circuit, which we call it as a to D converter or analog to digital converter. The the basic operations in the receiver are regeneration of the impaired signal, decoding and reconstruction of the train of quantized pulses or samples. So, regeneration it also occurs at intermediate points along the transmission path. Regeneration along the path it is necessary. It becomes necessary when you are doing the time division multiplexing. It is very necessary to synchronize the receiver to the transmitter for the overall system to operate satisfactorily. So, we'll use the pulse code modulation. So, we'll take each block one by one. The first is the sampling. So, the incoming message signal it is sampled with a train of narrow rectangular pulses so as to closely approximate the instantaneous sampling process. In order to ensure perfect reconstruction of the message signal at the receiver, the sampling rate must be greater than twice the highest frequency component W of the message signal in accordance with the sampling theorem. In practice, a pre-alias filter or a low-pass filter is used at the front end of the sampler in order to exclude frequencies greater than W before the sampling. Thus, the application of sampling permits the reduction of continuously varying message signal to a limited number of discrete values per second. This is about the sampling. Next, we'll take up the quantizer. The sampled version of the message signal. After sampling, you'll get the sampled version of the message signal. Now it has to be quantized. Therefore, providing a new representation of the signal that is discrete in both time and amplitude. The quantization process may follow a uniform law. In certain application, it is preferable to use a variable separation between the representation level. For example, the range of voltages covered by voice signals from the peak of loud talk to the weak passages of weak talk is on the order 1000 to 1. By using a non-uniform quantizer with the feature that the step size increases as the separation from the origin of the input-output amplitude characteristic is increased, the large end step of the quantizer can take care of the possible excursion of the voice signal into the large amplitude ranges that occur relatively infrequently. In other words, the weak passages which need more protection are favored at the expense of the loud passages. So in this way, a nearly uniform percentage precision it is achieved throughout the greater part of the amplitude range of the input signal, with the result that fewer steps are needed than would be the case if a uniform quantizer were used. The use of a uniform quantizer, it is equivalent to passing the baseband signal through a compressor and then applying the compressed signal to a uniform quantizer. So a particular form of compression law is used in practice and it is called the mu law, which is defined by the equation V is equal to log of 1 plus mu m divided by log of 1 plus mu, where m and v are the normalized input and output voltages and mu is a positive constant. So in this figure here we have plotted a mu law for varying mu value. For mu is equal to 0, mu is equal to 5 and mu equal to 100. The case of uniform quantization corresponds to when mu is equal to 0. For a given value of mu, the reciprocal slope of the compression curve, which defines the quantum steps, it is given by the derivative of m with respect to the v. So, dm by dv is equal to log of 1 plus mu by mu into 1 plus mu m. The mu law is neither strictly linear nor strictly logarithmic, but it is approximately linear at low input level, corresponding say mu less than or equal to 1, less than 1, and approximately it is logarithmic at high input values where mu of m it is greater than 1. So this is one law. Another compression law what we used in practice is A law. So according to that, V is equal to A of m divided by 1 plus log A, 1 plus log of A of m divided by 1 plus log A for different variations of A. So practical the plot is shown in this figure. This is A law. Practical values of A tend to be in the vicinity of 100. The case of uniform quantization corresponds to A is equal to 1. This is a uniform quantization. The reciprocal slope of this compression curve, it is given by the derivative of m dm with respect to dv, the output. So it is given by 1 plus log a by a for all the values of m between 0 and 1 over a, and it will be 1 plus log a of m for m between 1 by a and 1. Thus, the quantum steps over the central linear segment which have the dominant effect on small signals are determined or diminished by the factor a of 1 plus log a. So this is typically about say 25 dB in practice which is compared with the uniform quantization. In order to restore the signal samples to their correct relative level, we must use a device in the receiver with the characteristics complementary to the compressor. Such a device is called expander. Ideally, the compression and expansion laws are exactly inverse, so that except for the effect of quantization, the expander output is equal to the compressor input. The combination of a compressor and an expander, we call this as a compander. In actual PCM systems, the companding circuitry does not produce an exact replica of the nonlinear compression curve. Rather, it provides a piecewise linear approximation to the desired curve. By using a large number of linear segments, the approximation can approach the true compression curve very closely. This form of approximation will be discussed later. So next is the encoding. So in combining the process of sampling and then the quantizing, the specification of a continuous message signal becomes limited to a discrete set of values, and it is not in the form best suited to transmission over a line or a radio path. To exploit the advantages of sampling and quantizing for the purpose of making the transmitted signal more robust to noise, interference and other channel degradation, we require the use of an encoding process to translate the discrete set of sample values to a more appropriate form of signal. Any plan for representing each of this discrete set of values as a particular arrangement of discrete events is called as a code. One of the discrete events in a code is called code element or symbol. For example, the presence or absence of a pulse, it is a symbol. A particular arrangement of symbols used in the code to represent a single value of the discrete set is called code word or character. In binary code, each symbol may be either of two distinct values or kinds, such as the presence or absence of a pulse. The two symbols of a binary code are customarily denoted as 0 and 1. In a ternary code, each symbol may be one of three distinct values or kinds, and so on for other codes. However, the maximum advantage over the effect of noise in a transmission medium is obtained by using a binary code, because a binary symbol withstands a relatively high level of noise and is easy to regenerate. Suppose that in a binary code, each code word consists of R bit. The bit is an acronym for binary digit. Thus, R denotes the number of bits per sample. Then, using such a code, we may represent a total of 2 to the power R distinct numbers. For example, a sample quantized into one of 256 levels may be represented by an 8-bit code word. There are several ways of establishing a one-to-one correspondence between representation levels and code words. A convenient method is to express the original number of the representation levels as a binary number. In the binary number system, each digit has a place value, that is a power of 2. So we can observe in the diagram or a table here where ordinal number of representation level is from 0 to 15. 11 number expressed as a sum of powers of 2. 0 is expressed as 2 to the power 0. Sorry, it is represented with no symbol here. So the binary representation is 0, 0, 0, 0. Next number is 1. So the binary representation is 2 power 0. So binary number is 2 power 0 is what? 1. So 0, 0, 0, 1. Next number, it is 2. In order to have the 2, the level number expressed in powers of 2 is 2 power 1. So 2 power 1 is 2. So its binary number is 0, 0, 1, 0. Similarly, let me take a random number like 7. In order to have a representation level 7, it can be represented as 2 power 2 plus 2 power 1 plus 2 power 0. So 2 power 2 is 4, 4 plus 2 power 1 is 2, 4 plus 2 is 6, 2 power 0 is 1, 6 plus 1 is 7, so that is what is the number. So its representation is wherever we have a digits with 2 power something, so that will be taken as 1, and wherever we don't have anything in that place, we'll place 0. So it is 0, 1, 1, 1. Similarly, let me take 13. In order to have 13, you must have the representation as 2 power 3, that is 8, 2 power 2, that is 4. So it is 8 plus 4 is 12. 12 plus 2 power 0 is 1. So 12 plus 1 is 13. So it is 1101. So this is the representation 1101. This is how we can have the representation when r is equal to 4, means 4 bits are used. 1, 2, 3, 4. You can see the representation is having 4 bits. So this is one method of coding. So let me summarize what we have discussed in today's class. We started with pulse code modulation, its block diagram, what is the step-by-step procedure in transmitter, in channel and in the receiver part. And then we started with the first step, that is the sampling, then quantization. In quantization, we have to remember that we are using the law, that is compression law, mu law and A law, both we have discussed. And then we took encoding. So depending on the number of representation levels and number of bits, we'll have different number representation. So that we have discussed, and in next video we'll be discussing about the line codes, and then differential encoding, regeneration, decoding and filtering. Thank you.